do agrochemicals, insect pheromones, and pharmaceutical intermediates all have in common? They all can be made from a chemical reaction known as olefin metathesis. Olefin metathesis has evolved over the last few years into a mature tool for advanced organic, polymer, and bioorganic chemistry. In this video, I'll be talking about recent advances in Z-Selective olefin metathesis. Here is the summary of contents. First off, I will present a brief introduction of this topic, followed by its discovery, challenges and solution, recent advances, and finally, conclusion. What is metathesis? The word metathesis is derived from the Greek word meta, which means change, and thethemi, which means place. In chemistry, it refers to a chemical reaction in which one part of each two compounds interchange to form two new compounds. Now, what is olefin metathesis? Olefin is another name for alkene, a carbon chain with double bonding. It can be described as a transition metal-catalyzed reaction in which formally a mutual exchange of alkylidene groups between two substituted alkenes occurs. In another word, metathesis constitutes a catalytic method for both cleaving and forming C-C double bonds. For example, as you can see in this schematic diagram, one of the propene molecules exchanges its CH2 group for the CH3CH group in the other propene molecule. The result is butane and ethylene gas. A metal catalyst, which is not consumed in the reaction, is required for the reaction to occur. Powerful and highly tolerant new catalysts have been the key to this success. Metathesis was discovered as early as in the 1950s. However, the appearance of the catalyst at molecular level and how it works were still unknown. In 2005, Nobel Prize in Chemistry was awarded to three scientists, Yves Chauvin, Richard Schrock, and Robert Grubbs, for the development of the metathesis method in organic synthesis. Though many researchers put forward proposals as to how metathesis could take place, the breakthrough came in 1970 with a publication by Chauvin. Chauvin presented an entirely new mechanism for how the metal compound functions as a catalyst in the reaction. His new experimental results tallied with this new mechanism and could not be explained by any previously proposed mechanism. Following the proposal of Chauvin, a tremendous research effort of organometallic chemists has eventually led to the development of highly active catalysts. The breakthrough came in 1990 when Schrock reported the construction of a group of very active, well-defined molybdenum catalysts. Molybdenum catalysts are very sensitive to oxygen and moisture, but with the right treatment, they are very powerful tools in organic synthesis. Yet another breakthrough came in the year 1992, when Grubbs discovered the use of ruthenium metal as an OM catalyst. It was stable in air and demonstrated higher selectivity. Grubbs catalysts have become the first well-defined catalyst that has set to be a standard in which all new catalysts are compared. Although the search for more active catalysts has been a field of intense research, the challenging control of Z stereoselectivity has only been recently investigated. The first breakthrough in the design of Z-selective catalysts occurred in 2008, when Hoveda and Schrock published a paper on new molybdenum-based catalysts for enantioselective alkene metathesis. These mapped chiral catalysts serve as the basic prototypes on which all other Z-selective catalysts developed up to now are based. The general principle lies behind the formation of the alkenes is due to the inhibition by the steric proximity of one alkene substituent to the bulky axial ligand in the transition state. Moving on to the challenges. Internal olefins can exist as E or Z isomers. Owing to the higher thermodynamic stability of the E isomer, most methods of olefin synthesis such as the Wittig reaction, the Horner-Wadsworth-Amos reaction, and the olefin metathesis preferentially deliver the more stable E olefins. The formation of higher energy Z alkenes has generally been limited to ring closing metathesis in small ring sizes, where the ring string inhibits the formation of E alkenes. However, ring closing metathesis for the formation of macrocycles does not display this high degree of stereoselectivity. In recent years, a new range of OM catalysts has been developed to overcome these problems and enable formation of Z alkenes from simple, unfunctionalized starting materials. There are two main criteria of a catalyst capable of kinetic Z-selective OM. Firstly, the catalyst must be able to overcome the thermodynamically favored formation of the alkenes. Secondly, it is equally important that the Z olefin, once formed, does not re-enter the catalytic cycle through secondary metathesis, as further reaction with the metal alkylidine may give rise to the isomerization and furnish the thermodynamic E products. The above challenges have motivated the investigation of alternatives to the traditional alkylidine ligands. A study conducted by Smith and co-workers reported that monothiolate ruthenium indenilidine served as a promising Z-selective OM catalyst. The authors developed a complex bearing 3-phenylindenilidine, a ligand known to promote stability in other ruthenium-based OM catalysts. This complex also contains pyridine as a stabilizing donor ligand, which initiates catalysts rapidly and gives appreciable yields combined with moderate to high Z selectivity within minutes at room temperature. However, the design of this complex forms a configuration different from any other monothiolate-based OM catalyst. This complex contains three sterically demanding ligands, which are the NHC, the aryl thiolate, and the indenilidine. The steric pressure resulting from the three bulky ligands forced the thiolate ligand to position itself trans to the NHC ligand. The total steric pressure is larger than usual due to the indenilidine ligand, which prevents the cis coordination of the thiolate and the NHC. This configuration is expected to be incompatible with Z selectivity and initiate metathesis slowly, as pyridine might not readily dissociate when trans to a chloride. Surprisingly, even though this dissociation is indeed associated with a barrier, this complex initiates metathesis more rapidly and readily at room temperature. Besides, the complex is not only fairly long-lived and stable in catalysis, but they also can offer up to 80% of the Z isomer in metathesis homocoupling reactions. Moving on to the next recent advances. Within the last 20 years, it has been demonstrated that well-defined metathesis catalysts can also be immobilized onto surfaces and display good reactivity. Recently, Goldstein and co-workers investigated the use of a catalyst known as cationic molybdenum imidoalkylidine NHC complex confined inside the pores of mesoporous silica. Based on this figure, they believe that the pore wall or silica surface will act in a way that influences the transition states involved, in which the intermediate molybdacyclobutanes, as you can see here, pushing the two substituents, this is the substituent 1 and this is substituent 2, to the same side as each other. With smaller pore sizes, this effect will be further enhanced due to the smaller space available for the molybdacyclobutane, ultimately leading to the Z product. Upon investigation, the authors observed that this surface bound complex indeed display an increased Z selectivity, especially during the early stages of the reaction. This effect was influenced by the catalyst being bound directly to the surface of a silica material, where the proximity of the catalyst to the surface governs the transition state. Kinetic investigations also revealed that smaller pore sizes resulting in higher Z-selectivity at higher conversion, which is attributed to the faster diffusion of the product out of the pore. In conclusion, olefin metathesis is an organic chemical reaction that utilizes metal catalysts for the transfer of substituents between olefins. Generally, formation of E-alkenes are more thermodynamically favored than Z-alkenes due to their lower energy. Therefore, a precise and reliable catalyst design should be taken into consideration to proceed Z-selective OM reactions. Nowadays, there are numerous findings of Z-selective catalysts, such as the monothiolate ruthenium indene leading catalyst and the use of surface-supported organometallic catalysts. Both literature findings reported a high selectivity of Z-alkenes. That's all for me. Thank you for listening.